Computer audio. And so far, no one is joining from Zoom. Interesting. Yep.
I'm curious. I'm looking at the C code for this program. Does it actually do anything important? So this kind of uses thing.
Well, I cannot remember, so I'll be working on this as you guys work on it.
It's like it just does something. It's not really anything useful.
Well, that is entirely possible because the objective of the final exam is to see how much of the material you understand. So, all right, so it is time to get started. I'm gonna go ahead, and we got some people. We got one person on Zoom, and I'll try to maximize the screen as much as possible. The recording is on already, so that means you don't have to worry about not recording it. The tape is rolling, as they say. All right, so we'll just go ahead and start with this page. This is the instructions. I noticed in not only this class, but in some of my other classes, that people usually do not read all the instructions of an exam. Please do, because typically have something that is important. So other than the start time, the date and the duration, which you should know already. Also, the individual exams, you can use any material that you can prior to the exam, and so on. So that means we are exactly 1 week from the final exam. So that means as you review the material, you might want to kind of condense the notes into a shorter form. So this way you can refer to it. Okay. I would also advise people who are more visual to draw pictures. Okay. What is on the stack? Where is the return address? What are the parameters? Where are the local variables? What is LVR, LVS, okay, local variable size, and so on. So as you go through the material, prepare what you are going to bring to class. Okay, now you are still allowed to print anything from the class itself. So all the reading modules, all the sample programs that I did in class, any screenshot that you want to include, those are all legit. Okay, the question is, can you find the information in an efficient way? That is the question. Okay. All right. Comment the TTP ASM code to show that you know how to relate the assembly code to the C code concept. This may earn partial credit with a may here. Okay, so because it depends on the context. Okay. Now, explanation does not mean if you have a CPR AB instruction. If someone did just say, register A is copied to register B is copied to register A, that is worthless. Okay, because that I know already. You kind of have to say, what is in register A? In an LDAA, you have to end up saying, okay, A is now, how is it related to a construct in the C or the C++ program? Okay, so that is what I'm looking for. Relating the assembly language constructs, the registers, memory content, locations, and whatnot, to the C program itself. All right. So in this case, I also supply the commented out C code. You're provided with an erroneous implementation. Yes.
Is it possible to try to engineer the test so we have the C++ code and the?
I believe this one does have the C code interleaved. I mean, I have to take a quick look at it.
Oh, yeah, it includes
it does.
If it does, can it be on 2 different sheets of paper or something? So we might compare it next to each other.
How about this? I'm going to use a paper clip so you can separate the pages. Yep. I can give you the C code on the page if you want to.
Yeah, that'd be best.
Your job is to identify the bugs. Okay. In other words, I will give you a intentionally faulty in the tricky way. Okay. Assembly language implementation of the C code. Then your job is to figure out where those bugs are and fix it. Is that okay? Yep.
So the C code itself is going to be correct, but the assembly will have a bug.
Yes. Yep. Well, the C code is no correct versus incorrect. It is syntactically correct at least, but the implementation of the C code is wrong. So unless I tell you what the C code is supposed to do, like this is bubble sort or this is insertion sort, there's no right or wrong associated with the C code itself because it doesn't have a particular objective. But I want the assembly code to be implementing the constructs, what the C code is describing. So that is the key. Yep.
Okay, so just to clarify, there are no errors that we have to fix in the C code.
That is
It
right.
doesn't fix the errors in the assembly, so
Yep.
that the assembly functions exactly as the C code.
Yes. Yep, exactly. Okay. So identification. Okay, so identification is what is supposed to be done, what is actually done instead, because that is how you identify a bug, because there's a difference between what the C code is describing and what the assembly code is doing instead. Use comments to relate the assembly language code with the C code. This means all the registers involved with the error, if any, should be tracked and explained to the point of the correction. So basically, this is not extra work, okay? Because you're going to need this in order to figure out how to fix a bug, because you have to track what is in the register. I can tell you, even though I write the test, I cannot track the registers. I have to rely on like comments or piece of paper so that I can keep track of which register has what. And there are only 4 registers too. Okay, and the stack pointer is not even one of the things that I have to track. The register D is always the stack pointer. So we only have 3 registers to track in this architecture. Explain why the expected work is not done and how to fix it. Okay. Do not change code that is correct to begin with. Such changes will get points deducted as they indicate a lack of understanding of the concepts. So I will give you certain alternative sequences of getting the same thing done that we might have used in this class. In other words, in this class, I might use a very consistent pattern to get something done. And then in the test, I'll give you a sequence of instructions that will get the same thing done, but the sequence is different. So you have to look at that and go like, you cannot just say, oh, this doesn't fit the pattern, it has to be wrong. I'll replace it with a pattern that we have been using in class. That would not work. Okay, so you have to basically be careful and look at those and say, okay, this doesn't look like a pattern that we have used in class. What does it actually do? If it does the same thing, then it's not a problem. Yes.
So even if, okay, so let's say there is a problem.
Yep.
But we solve it in a way that also dismantles some of the useful code that is correct. And then, but it still works exactly as planned. It's just needed in a different way than was intended.
I think if you make more changes than it is necessary, then you might get what's deducted. It depends on the context and depends on the extent of what is getting modified. So if somebody looks at my code and goes, I absolutely cannot understand what you're doing and just re-implement the entire thing, that would probably not count as a good answer. Okay. And there are situations where there are multiple fixes, and one would involve changing one more line. Okay, that's not a problem. It's only when people rewrite an entire block of code unnecessarily, then it becomes a problem. Okay, so moving on. To explain, use comments to relate a register to concepts in the C code as much as possible. I think this is like the 3rd time this is mentioned in the instructions. To remove code, cross it out and explain. Okay, since this is done on a piece of paper, you do not need to know how the shortcut keys of the effect of crossing out something, right? So you just use your pen or pencil, cross it out, and then replace it with whatever code that is supposed to be there. Or if it is extra, if it's not supposed to be there, just cross it out and explain why you cross it out. To change code, you can edit in place, which means you just kind of cross out certain things within an instruction and say this register instead of register A should be register B. But then you still have to supply the explanation. To insert code is easier on a piece of paper as well. I'm not sure whether you can understand my air gesture. Okay, I will try to do an air gesture using a mouse. because there are people online. So if you understand, do you see what I mean? This is typically how people write, okay, this code inserts into here. So you can use arrows, okay? Yeah, exactly. It's just a symbol like that. And or you can use a piece of arrow. So you just have a block of code, and then you use the arrow to say, this is where the code needs to go between this line and this line. So any way that I can understand is going to be okay. Okay, so all you have to do is to make sure that it is something that a person, an average person would understand. All right. So the following is the C code. Okay, so we'll start with the C code here. So the C code has a structured definition called strf. And within strf, we have three members. We have ppref, or pointed to the previous. We have n, and then we have k. So those are the three members of a structure. And then we have done as a subroutine starting on line 55. It does certain things. And then we have function f, on line 60, that's also doing something else. Okay, a little bit of code here. And then we have main, on line 75, that's basically just the entry point of the entire program. It allocates the space for a particular structure and a local variable y. Do some initialization with the structure x, and then call f, and then return 0 at the end. Okay, so that's the C code. And as you can see, it is not that long. And I would say it is not any more complex than your homework assignment, even though there are some relationship between the two. In other words, in the discussion of this particular past exam, it might give you some idea of how to work on the program that you need to turn in on Thursday. Okay, so we'll continue with this. All right. All right, so right here, okay, we have the no op, at the beginning of the program, which is necessary if you want to use River Spider, to trace the program. But otherwise, it doesn't do a single thing. It is not an error. Okay, it is not a mistake. It just doesn't do anything. This is how we initialize a stack pointer, and then this is how we call a subroutine. Okay, this is the return address. We decrement the stack pointer. We store it over here, and then do a JMPI to main. And then when I scroll down further, it becomes the entry point of gun. Yep.
Are you missing a halt instruction?
We are missing a halt instruction right there. Yes. So now you have to say, why do we need a halt instruction right after line 91? What happens if I do not have a halt instruction there? So that's how you want to explain it. Okay. So does someone want to do this? Explain to me why we need a halt instruction after line 91. Yep.
Make sure that the code actually stops.
Because without a halt instruction, what will you do? What would you do?
It just keeps running each register over and over.
It would run into done as if done is a part of the main code. Yeah, that is correct. Main as in, the entry code, not the main function code. So you're correct. So we need a halt instruction here. Okay, so then you have to explain it. Okay, and I just did my explanation verbally, and I just kind of say, you have to explain. All right, so now we are looking at the struct definition, and that has to be consistent with the C code. So that means, I should probably do a V split in this case. So now on one side, I can focus on the C code. On the other side, I can focus on the assembly language code. Yep.
Is it possible when you're writing those comments for like the errors, can you just like label them as like error, explain or something like that? Just so when we're looking through, we can remember which ones are errors.
I was trying to entice you guys to learn how to use diff. Diff, D-I-F-F. It's not differential equations. I know what you guys are thinking about because I think that's the only thing some certain people in this class is thinking right now. So diff is a utility program that can allow you to compare two text files, and it can display the differences in a variety of ways. So I'm just going to do it like this, and then later on I'll explain how to use diff, because I think it's a really useful tool, even for attempt to write the program that's due on Thursday, because you want to keep track of multiple versions and then also know, okay, this used to work and now it's not working. What did I do to mess up my program? That's what diff can come in really handy. So remind me to talk about diff, at the end of this class. But since the original version is already in the announcement, I can always use that version to compare to the modified version. So I would do that at the end of the class. All right, so I want to compare the structure definition to the structure definition over here. P-pref is the first one, okay, that looks correct. N is the next one, K is the one after that, and then the size is the offset to the last member plus the size of the last member. So everything looks good because a pointer only has 1 byte. U in 8_t only uses 1 byte, and then U in 8_t also uses only 1 byte. So that looks good to me. And now we are looking at done. So we are focusing on line 55. And so we want to look at this code here and say, is that doing what done is supposed to do? So the first thing we need to do is to check whether the label definition corresponding to the parameter PF is correct or not. It looks correct to me because the stack pointer points to the return address and 1 byte above the return address, which is what the stack pointer is supposed to point to, and the entry point of the subroutine is the parameter PF in this case. So that definition of 1 here is indeed correct. Are we still doing okay so far? Any questions? Yes.
I just have a question about the done function. Does that return a bool?
It does return a bool because there's a bunch of bools. Yep.
Can you explain one more time why we don't use both PF and why we established it a little more?
Because it is corresponding to the only parameter to the function. And all the parameters are pushed by the caller before the return address is pushed. So the return address being the last thing that was pushed on the stack means the stack pointer will be pointed to the return address. So that means that all the parameters would be at locations above the return address. And since we only have 1, it is right past the return address. All right, so we have now checked that. So I'm going to go line by line and use the text cursor to help us, keep track of where we are. All right, so according to the C code over here, we want to know whether the N member of the structure that is pointed to by PF is null or 0 or not. So that means the first thing I need to get to is PF, the parameter. So in order to get to anything that is on the stack, that would include parameters as well as also local variables. We need to get the offset, add the stack pointer to the offset, then we get the address of that thing that is sitting on the stack. Then we have to dereference it to get to the value of that thing. So we have the offset, we have the address, now we have PF itself in register A. That seems correct to me. So I have double checked these 3 lines of code. And then we have to say, well, what is A at this point? What is register A on line 104? It is the pointer, it is a point, that's the type here. It is a pointer to a struct strf. Okay, so what do we do with it? Well, we'll decide what to do with it later, okay? Because what we really want to do is not to access the structure itself, but to get to one of its members. So how do we get to a member of a structure when we already know the address of the structure itself? We just have to add the offset of that particular member, which is now loaded in the register B, and then add the address of the array, which is the register A on line 107, to register B, which is the offset. Then register B becomes the address of the member that we need to access. Is that okay? Okay. So on line 108, by the time you're done with 107, register B becomes the address of member N of the structure that PF points to, which is not what I need because I want to get to the back. So that's why we need a dereference on line 108. So now register A becomes the actual value of member N of the structure that PF points to. The AND AK instruction, by this point, it should be, it's kind of like a template. If we just want to know whether something is a 0 or not, that's a quick way to do it. There's no need to compare to 0. And then after that, the only thing we can do is a JZI. You don't have to say NZI. So if it's 0, we go to one particular place. If not, we continue the execution. Now, this is where I cannot keep talking and I have to start commenting because I need to keep track of the program. I actually intentionally did not prep for this class because I want to show you if I was to take this, take this test, this is what I would have to do too. So I would have to look at this and say, okay, if PF points to N is indeed 0, go to done ret 1. Okay. And the label name seems to suggest that would be the right thing to do because if PF points to, if N of the structure that PF points to is indeed a 0, this should return a non-zero. And guess what? 1 is a non-zero, so turning a 1, as the label implies, seems to be okay. Okay, now whether I actually do that at that label, I'll check later. Okay, but at this point, this seems to be correct. So I would also comment here and say that, if I do fall through, what that means is PF points to N. Oh, forgot to specify the N here. That is not 0. Oh, okay, well, that's fine, because that means that now I have to look at the second condition and look at the member K instead of the same structure. So all of this time, register A is now gone. Okay, register A is no longer the address of the structure itself because I clobbered that, when I did this over here, when I did the LD instruction on line 108. So that means, I might need to do some work to get back to member K. So member K, so now what is this line doing? Yep, go ahead. Question?
Shouldn't that line just be, we should just load SDR FK instead of the step to the right?
Which line?
112.
On line 112. Should we, what should we do?
Load SDRK and stuff from the C.
Well, we'll check out what the assembly code is doing first, and then we'll try to figure out, whether it's working or not. So register B is still pointing to member N of the structure that PF is pointing to. Okay, so let me just kind of write this down. Okay, so I'm going to specify here and say B is the address of PF points to N. Are we good so far? Because we just added the address of the entire structure to the offset to the member of the same structure. And hence we end up with register B ends up with the address of the member of the structure that PF points to. So now D has never changed since this point. Okay, ever since line 107, register B is maintained. So what am I doing here? So what is, by the way, what is C? What is register C? This is a postfix notation. So what would it look like if it is a normal infix notation?
Does it represent the offset between?
Yep. It is basically saying if I need to go from N to K, how many bytes do I need to move? Okay. So it's the difference between two members of the same structure in this case.
And I assume this is just because you said you were going to do things in a non-standard way to test different things. But couldn't you just, would this also work if you just took if you took B and then you added STR?
Nope, it won't work because B is no longer the pointer of the structure itself. It is now a pointer to a member of the structure. So it would not have worked. Now, if I did copy, this A to register C, then I could use register C at this point and say that is the address of the structure itself, but I did not. Are we still doing okay so far? I mean, if you want to draw a picture, I can do so.
I think it's fine.
Okay. All right, so this is one part where, if you are a more visual person, a picture would definitely help. Okay, I can actually do that in line. Okay, so let me just do that in line here. So we have a structure. The structure has 3 members. We know that K is the last one, N is the second to the last one, and then the first one is P prep. So when I do it like this is the highest memory location. This is the second highest memory location. This is the lowest memory location. So what we do have here is we have register B pointing here. But I'm not interested in N anymore. I'm interested in K because the code in the C code here needs to access the member K and not member N anymore. So the question is, how do I go from here to here? So P SCRF underscore K would have been 2. STRF underscore N would have been 1. So that means when I do this subtraction here, register C would end up with a value of 1, which is exactly the number of bytes between member N and member K of the structure that I need to access. I already know where to find member N because register B has the address of member N. So if I just add 1 to register B, what's going to happen? We get to member K. So that's the, what I referred to earlier as, I can do it this way. I can get to the address of a different member of the same structure just by, doing the subtraction. So here's the question for you. Okay, if I choose to change the ordering of the members and update the label definition accordingly, do you think this code here is sensitive to changes to the structure, or do you think it doesn't really? It's not sensitive because all it is really just calculating the number of bytes between 2 members. So it would work, no matter how I reorder the members, as long as the offset of the members, which are defined in these particular labels, as long as those are consistent to the C code, this line of code would survive a changing of the structure itself or changing of the definition of the structure itself. Okay, so that's kind of important because, I want you guys to think about all of these things. So by the time I'm done with this one here, register C would have become the address of the member K. Oh, yep, and member K of whatever structure the PF is pointing to. And then, okay, so I do an ANCC right away to see whether that is 0 or not. Do we smell a bug? I think that's a stink bug because we can smell it. Okay, you guys may not get the joke, but that's okay. So, so what do I need here? If I want to do the minimal change, yes.
CC.
Yep. So we have to insert L load C over here so that C becomes the actual member K of the structure the PF is pointing to. Okay, so remember, the diff utility program, that I talked about earlier, it can basically go back and say which lines has changed in what way, so we can quickly identify these changes later on. Okay, so that solves that problem. And if it is a 0, we go to the same return point, which is done returns 1. That seems correct to me. So now we have compare AC. So compare AC is attempting to perform this particular comparison. So now we have to keep track of what is in register A, what is in register B, and what is in register C. What is in register A at this point? What was the last time that we updated register A? You should be able to see that line from here. Yep.
The dereference of the pointer to N. So the value of N.
Which line? What was the last line that we?
Loaded on.
Yes, okay, well, yes and no. Technically speaking, 109, 109 actually, overwrote register A, but with its original value, so it's not actually changing anything. So you're correct. So technically speaking, it should be 109, but for all practical purposes, it's 109. So after that, what do we have put into register A? In other words, what am I checking whether it's a 0 or not?
You're checking to see if the Z5 is. Right.
That is correct, but from the context, what am I checking? What is this checking? It's checking whether something is a 0 or not. I mean, this is giving it away, right? So that means register A did have member N of the structure that PF points to by the time we get to line 120. Okay, that's good. Are we supposed to compare to register C? What is in register C at this point? We just mess around with register C. Register C after this does have the value of member K of the structure that PF points to. So we are indeed implementing what the C code is supposed to be implemented. Okay, all right. So we do compare, and if the compare returns a 0, which means A and C are the same, then we go to the same point to return a 1. Otherwise, we return a 0, and then we go to just return, and then we have done return 1 as a label, and we load a 1 into register A. Well, that seems correct. I mean, the label did say we want to return a value of 1, and then we get to the return code here. I would not make the assumption that, oh yeah, those are the 3 typical return instructions. I would double check. Okay, so I'm gonna double check. Register D is the stack order. I'm popping these 2 instructions, will be popping whatever is on the stack right now, which should still be the return address, because I didn't push anything in this entire duration. So the stack pointer should still be pointing to the return address, and then I jump to what the return address is. Okay, that seems correct to me. So now we are done with done, no pun intended. We are moving on to function F. So we'll move this side as well. All right. So since somebody asked, whether this program is absolutely doing nothing meaningful, the answer is no. This program is actually doing Pascal's identity. So if you're taking 440 with me, then you should hopefully identify this as the Pascal's identity function. The way we calculate the number of combinations in a recursive way. That's basically what it's doing. Okay, first thing first. Okay, we got PF. We also have a bunch of local variables. We got local A, local B as structures. And then we also have result as an unsigned 8-bit integer. So the question is, does that look like how the stack should look like after we allocate for the local variables? So the locations are not really that important as long as it is on the stack and we have enough space for each one, it should be fine. So local A is the lowest. That's because I would look at the ordering of how I declare the local variables, and whatever is declared first has the lowest address. So that's just one convention to follow. It's not the only convention. Okay, so local A is the lowest, fine. Local B is F local A strF size plus. So that means I'm allocating for the number of bytes that the strF structure will require for STRA. That sounds right, because they are not pointers. Local A and local B are not pointers to STRF. They are STRFs. So they are not single byte things. They will take as many bytes as a structure or a struct FDRF would take. Yep.
So on the test, if we want something like this, do you want us just to use the arbitrary kind of STRF size? Because we don't know the actual value.
It is defined. So STRF is actually defined. Let me look for that. STRF underscore size. It is defined.
Okay.
And we checked this too. We double checked that this label is indeed correct. So we actually did that already. All right, so local B is another structure. So that means the result, which is a local variable after that, should be the offset local B plus the size of the structure of the type FQRF. That seems correct. F underscore LBS, local variable size. In other words, how many bytes altogether do we need for all of these local variables? Well, we have to add 1 to F underscore result, which is the offset to result. This is the size of result itself. That seems to make sense because it is only an 8-bit unsigned integer. So that calculates the total number of bytes that we need for all the local variables. Go like, yep, that makes sense. PF is the parameter, which is pushed by the caller. So that would be the first thing, in the entire frame that is pushed on the stack post. So that's why it has the highest address because it's pushed by the caller. And it is F underscore LBS 1 plus. This 1 has to do with the return address. I don't need a label for the return address because I don't need to access the return address. Okay, so that's why you this 1 plus 3. So that we move on. So the label definitions seem to be all correct to me. And now we move on to line 40 and line 41. So together, these two lines is basically decreasing the stack pointer by F underscore LBS as an amount. Yep.
Is the label FLBS, is that doing the same thing as making that label the return address?
Yes.
It is.
Yep. So F underscore LBS is also the same as the offset to get to the return address. That is correct. All right, so this is for allocating all the local variables. That is correct. But in my typical way of thinking, I want to look for the closing first. So I'm going to scan and look for the end of the subroutine and look for a matching increase of that. Okay, which I find here. So now I know I'm allocating. I'm also deallocating the local variables. And right here, I'm noticing something that is odd. Where's the code to return to the column? It's entirely missing. Okay, well, since I spot it now, let's fix it now. So now we fix that. And because F does return a value, so I cannot use register A. Register B and C are fine. I can choose in one or the other. So I can now say LD, DD, increment D, JMP B. So these three lines are inserted, okay? Inserted to return to caller. Okay. So now I have spotted another problem. And now it's time to go into the actual subroutine, the logic of the subroutine, to see whether the C code and the assembly language code are consistent. So in this case, I do leave behind the C code. It is sprinkled within the assembly code. That makes it a little bit easier for you guys to figure out, oh, so what are these lines implemented? So that's why I sprinkled the C code into the assembly code so that you can tell, oh, so line 144 to line 147 are supposed to implement, the result equals to 1, okay, in the C code. Do we have any questions about how the C code is interleaved with the assembly language code? Is that good? Okay, all right. All right, so let's see whether that works or not. Okay, we got the offset on line 144. We got the address on line 145. We have the right-hand side of the value of 1. And then we store the 1 to the address of result, which is my local variable. Seems okay to me. All right, moving on to the next part. Okay, so the next part is from line 149 all the way to 162-ish, okay? So that is implementing the conditional statement. So the conditional statement has to be called done first, and then negate whatever done has, interpret as a Boolean value to determine whether we want to go for the then branch or not. So I'm not going to worry too much. I'm just going to be, right now, I'm just going to focus on, are we calling done correctly? Are we passing the argument correctly? Are we calling correctly? Are we fixing the stack correctly after the call? Okay, so that's what we're going to do. 150, line 150 loads the offset. That's good. 151 calculates the address of PF as my parameter. Looks good. 152 is loading the value of PF to register A. Looks good. Lines 153, 54, and yeah, line 53 and line 154 is pushing PF on the stack. So those are all looking good, okay, because we're just pushing PF on the stack because it is the argument. And then we need to push the return address on the stack. So now we're looking at this code and go like, that pattern looks a little bit different from what we usually do in class. Instead of doing an LDI A.6 plus and decrement D, now we reverse those two. And instead of a .6 plus, we have a .5 plus. So if somebody correct this, and cross these two out, or just cross out this one and move it over here and say it should be LDI A.6 plus, that would get points deducted. Because this particular sequence works just as well as the other sequence. Nobody has any questions about it? Then we shall move on. Do you guys understand why we have a .5 plus this time? Byte 0, byte 1, byte 2, byte 3, byte 4, byte 5. Still works out. Is that okay? All right. So, and is it okay? Is it really okay for me to exchange the order of the decrement D instruction versus the LDI instruction? Would it cause any interference? No. Does decrement D need to use register A in any way? No. Does LDIA need to use register D in any way? No. So those two instructions have no interdependency, which means the ordering is not important. The constant that you put into register A is important because it really changes the offset between the LDI instruction on line 156 and the return point, which is on line 159. So that is the only part that is important. And it also explains why we changed the 6 to a 5. All right, so we look at those instructions and go like, yeah, we're pushing the return address on the stack. Then we call done, okay, we continue execution at done. When it does return, we increment D to get rid of the argument that is still sitting on the stack. And then we perform the AND AA, because after all, we just want to find out whether the return value, which is now sitting in register A, is null, is 0 or not. If it is 0, we go to the then portion according to the label. Yeah, we are going to the then portion. That seems correct. Otherwise, we go to the end of the conditional statement because there's no else to this particular if statement. So that all look fine to me. Are we still doing okay up to line 162? Right? So now we get to line 163, which is the entry point of the then branch, which is going to implement line 66 all the way to line 70 in the C code. So now we scroll up a little bit, okay? And you'll see whether it is being done or not, okay? All right, so we focus on line 66, okay, because that's the first one that we need to implement. Line 166 loads the offset into register C. Line 167 computes the address of PF and put it into register C. Line 168 is getting the value of PF, which is appointed to a structure in register C. So those all seem good to me. And then line 169 is loading the offset from the beginning of the structure to member N into register B. And then 170 is computing the address of member N of the structure the PF is pointing to in register B. That all seemed to be good. And then we have line 171 doing a decrement B. What is a register B again? By the time we get to line 171.
In register B, it has P F pointing to N or arrow N.
Okay, so let's be more clear. Does it have the address of the member or does it have the value of the member? It has the address of the member. What am I doing decrementing? What am I doing subtracting one from the address of the member? That's not what I need to do because I need to subtract one from the value of the member. So what is missing? The reference, which is LDBB. That's what's missing. Okay. So this is what I meant when I said, we really have to it would be helpful to track what is in the register as you move, to read the code. There's enough time to do it. Okay. I know it sounds really tedious, but it's not because you can just use the C notation. You don't have to write full sentence. You don't have to write in a full sentence that register B now has the value of member N of the structure that PF points to. Nope, just use the C notation. It doesn't take that much time. Yep.
In the exam, we should only expect one C code to like decode or like to fix the problems. But we only get one problem for the whole exam.
Yes, there are multiple flaws in the program. Which means you can get partial credit, because if you spot, let's just say there are 12 problems. If you spot 10 of them, you get 10 out of 12. So also sometimes when people spot a problem, they would identify this as a problem, but if they cannot find out how to fix the problem, it will still be partial credit for that particular problem itself. So yeah. All right, so decrement would be, yep.
Will the program be about this long?
Yeah, I would say so. Okay, so we have B being the right-hand side at this point. We just have to store that to member N of local A. All right, so from line 174, we are now dealing with the left-hand side of the assignment. So now we want to see what is going on here. So this one is a little bit interesting because I'm combining the offset to member N and the offset to get to local A as a local variable in one single expression. Is that really okay? The answer is yeah, it is perfectly okay because local A is not a pointer. Local A is the structure itself, from the C perspective. So the label of F underscore local A is the offset to the first byte of the structure already. And then strf underscore N is the number of bytes between member N and the beginning of a structure. So together, this becomes the offset from where the stack pointer points to member N of the structure local A. And for this one, I specifically asked people to explain what is in register A at this point and express that in the C concept. So in this case, it would be the offset of member N of local A as a local variable from where the stack pointer points to. Is that okay? So that is a specific point where I need an answer. So I added the offset of the member. I added the stack pointer to the offset, and therefore A becomes the actual address of the member. And then I store B to A to accomplish the assignment on line 66. Yep.
So when you say explain, we could just say the offset of local A dot N.
Let me give you a way to do it. Okay, so the answer can be A equals to the address of local A dot N minus the stack pointer. Or you can use SP for the stack pointer. As long as I understand it, it's fine. Or if you also want to use offset from where the stack pointer points to and that. I mean, obviously, I would have chosen just, that thing minus D because it's a whole lot more concise. Is that okay? All right. So I'm gonna go back to the more concise form like that. All right. So once you add D, it becomes the address of, and then you store to, the address. That is correct. That's how we use the left-hand side of an assignment. So that's done. Now we move on to line 179. And that will be corresponding to line 67. So let's check out what's happening here. All right, so we are dealing with local B this time. That is the left-hand side. And you can see how the right-hand side are exactly the same. So that means that there's really no need to recompute the right-hand side. And the right-hand side is still in register B. All we have to do is to recompute the left-hand side. And this time it is member N of local B, member N of local B. Remember to add the stack pointer to the offset. So the register A now becomes the address of member A of local B. We store B into it because B still has the right-hand side from line 66. So that's a pretty easy one, done. And then we move on to line 68 in the C code. And in the assembly code, it is on line 185. So we'll check out whether this works or not. Okay, let's figure this out. So we put the offset from the beginning of a structure to member K into register B. And then we add register C to register B. So now the question is, what is in register C at this point? See, it's important to track the registers because, I can utilize a register later on. So now we have to go all the way back and say, when was the last time we deal with register C? It was all the way up here. Okay, so at this point, what is in register C? And that goes all the way back here. So the question is, what is in register C at that point? That was the very last time. Nope, that was, okay, line 168 was the last time we changed the register C. And register C remained preserved all the way up to the point that we were asking a little bit earlier. So what is in register C on lines 168? Yep, the value of PF, okay? So it is the value of PF, okay. So knowing that, we get back here, and I'm gonna remind myself, okay? C has PF in it. So PF is pointed to a structure, which means it is the address of the beginning of a structure. Register B contains the offset from the beginning of a structure to member K. So that means when I add register C to register B, I do have the address of member K of the structure. In other words, yeah, I'm accomplishing that. Well, okay, the address of, and then we do a dereference, we get to the value. So by the time we are done with line 187 of the assembly code, we would have accomplished the right-hand side on line 68. Are we doing okay so far? All right. And then we move on. Okay, so because we have to do the assignment. So the assignment is using the same pattern as before. Load the offset, the sum of the offsets between the local A, which is the local variable, and it is a structure, and the offset to member K from the beginning of the structure. And then we add the stack pointer to it. So by the time you're done with line 190, register A would have the address of member K of local A. And then we copy register B, which is member K of the structure that PF points to. We use it to overwrite register, whatever register A is pointing to, which indeed is K of local A. And that is what we want to do on line 68. Are we still doing okay? Yes.
So for the assembly code, are you like Like, are you like staying like consistent, like with how you're assigning, like, are you gonna do the right side always first and then the left side?
Not necessarily.
It just looks convenient.
No, not necessarily. So you kind of have to, figure out which side is which side. It should be relatively obvious most of the time, because the store is going to give you a hint, unless the store instruction itself is faulty. So you still have to kind of double check, what is in the register, and then by the time you get to the store instruction, you have to double check and make sure that register A is indeed the L value of the assignment operator, and then B is the right-hand side. All right, so we are now down to line 9. All right, so we decrement B. So what is B? Register B, the last time we dealt with register B it is member A of the structure the PF points to. Okay, this guy over here on line 68. And the right-hand side of line 69 says, okay, for this one, we want it to be one less than the previous line, and hence the decrement B. Okay, so that looks good as the right-hand side. And then the left-hand side has the same structure as before. We are storing to member K of local B. And then we remember to add the stack pointer to the offset, okay? And then we do the store. That seems okay to me. So by the time we are done with line 198, we are done with line 69 of the C code. Are we still doing okay so far with this code? All right. So now we move on to line 70. Yeah, we're almost done. Almost. So line 70 is has a few things that it needs to do. The last thing that we need to do is the assignment, but I'm not worried about that because until I get to the sum of these two, I don't have anything to worry about the assignment. But the sum has to do with the call to F with local A and the call to F with local B. So I have to call those two things here separately and then add up the return values of each one. Does that remind you of the Fibonacci homework assignment? Yep. So we're going to look for those things, right? To make sure that we access the local variables correctly in this case. Now, when you are using an addition, okay, like this one here, whether you compute the left-hand side first or the right-hand side first does not matter because addition is commutative in algebra, so you can do it either way. So I just decide to call the handle the left-hand side of the addition first. So let's double check to see whether this makes sense or not. This is the offset to the local variable, local A. We're adding D to B, so B becomes the address of that thing. And then we load BD, and then we push that on the stack. Okay, well, there are several things are wrong here. How many things are wrong? There are at least two things being wrong here. What are we supposed to push on the stack? On line 70 of the C code. Are we supposed to push the entire structure on the stack or the address on the stack? Yep. We're supposed to push the address on the stack. So at which point of the assembly code do we have the address of local A in the register? 202. So that means 203 is not supposed to be there. Okay. Well, maybe it is. Because, well, okay. What we are pushing on the stack is definitely wrong because we are pushing register A on the stack when register B has all the things that we need. So how do we fix this? The quickest way to fix this is to fix both lines. But I think later on, I'm just looking ahead a little bit here. Yeah, so we can fix we can get rid of this line here, okay? And also change this one to use register B. Okay. So that will be double check. Okay, we got the offset, we got the address, and then we push the address on the stack. That looks good to me. Yep.
I was just.
Oh, okay. All right. And now we have that, the call, pushing of the return address. So this one is definitely here to kind of see if you guys can catch it, okay? Because the previous time we had the .5 plus and it was okay. This time it is not okay because the LDI is ahead of the decrement instruction. So the quickest way to fix it is simply to change the 5 to a 6. Because of the ordering between the LDI instruction and the decrement instruction. Okay, well, push it on the stack, continue execution at F. When it comes back, we increment D, and then we decrement D again, and then we store register A to where register D is pointing to. So can someone remind me what lines 20, 221, and 212 are doing? Because it seems kind of odd that we are pushing something on the stack when we are not calling anything at this point. We just got back from calling that.
The return value there.
Yep, it's the return value of f of local A that is being pushed. That is the same trick that we used in 2 programs already. The Fibonacci program requires this little trick, and then the 7, 5, 12 program that I illustrated in class also utilized the same trick. So that is the trick here. All right, so what we do next is to call F again, but this time with the address of local B. So we have the offset, we have the address, and once again, I'm pushing the first byte of the structure on the stack. Not good, okay? So this needs to be commented out because we want to push the address of local B on the stack, not the first byte of the structure on the stack. Then we decrement D, store C to where D is pointing to, which is just a push. And then we have, we push the return address, and this time it is correct because we decrement D first. So this one is correct, okay? The .5 plus is okay. And then we do a JMP I to F, we call F. When we come back, we clean up the stack, okay? We get rid of the argument that is still sitting on the stack. And then what do we do? And then I ask you after this instruction, what is the register B? In other words, what is the stack pointer pointing to on line 223? So after a call, okay, when the subroutine returns, we return to line 222. We increment D, okay, to clean up the argument that is still sitting on the stack. So after we clean up the argument that is still sitting on the stack, what else is the stack pointer pointing to at that point? What did we push earlier? Remember line 211 and 212, we push something on the stack.
I was just gonna mention anything else. Why is this here?
So this is pushing F of local A on the stack, right? Have we cleaned that up? We have not cleaned that up. And that also, reminded me that I have one more problem to fix that I just forgot to fix, which is a 1 plus here. Because I pushed one more thing on the stack. So the offset between where the stack pointer points to anything else on the stack is now 1 byte off. Because those labels are computed based on the assumption that we are just done allocating for all the local variables. But since we pushed the return value of f of local A at this point, or by the time we get to line 213, so that means we have one extra thing on the stack now, and the stack pointer is now pointing to 1 byte below the assumed location when we did all the label calculations. So that's why the 1 plus here is necessary to account for that one extra byte that is now on the stack. Okay, so I almost forgot about that one until I get back to here to try to explain what is still sitting on the stack. So what is still sitting on the stack right now is f of local A. That is what B ends up with after the LD instruction, and then we do increment D because we are now popping it. Is that okay? This is a pattern that we have seen already in the 5, 7, 12 program, as well as the Fibonacci program. Because well, it sounds like it kind of went. Okay, it's all right. Okay, so getting back here, so register B now has F of local A, register A has F of local B. So we add those two. So now we have the right-hand side done. And then we're supposed to store that to F result. So this is the offset, this is the address, and this is the storing or the assignment. That should be all good. And then we get to the end of the conditional statement, which marks the end of this curly brace here. And then we just have to say, put it into register A, offset, address, value. And we're done. Okay, we have now specified the return value. And then it's time to deallocate the local variables, which we checked already. Okay, we checked earlier, and also the actual code to return to the caller. All right. So are we still doing okay? Are there any questions up to line 243? Okay. So now we get to the main program, which is also subject to contain bugs. So now we get to main, and then it's not long. Okay, this one is mostly just about the allocation of stuff and whatnot. All right, so we look at the C code. We have two local variables here. One is X and one is Y. X is a structure. Y is just an unsigned integer. Yes.
Wait, can you scroll back up a little bit again?
Sure.
The OI numbers are different.
Oh, right.
Just do a little bit more. Okay, so did you just add those 3 lines?
Which?
What would be the, oh, we love that we added.
Yeah, yeah. So that's what I do. Okay, what you want to do is up to you. What I usually do is I look at the beginning of something and I look for the end of the something. So this way I don't forget to check the end of a construct that started way earlier. But whether you want to do the same thing or not, it's up to you. All right. Any other questions? Nope. Okay. So we are now going to main. So we have X being the first declaration, and therefore it is at location 0 or offset 0 from where the stack pointer points to after the allocation of local variables. And then Y is only 1 byte after X. Yep.
Shouldn't that be the size of?
Yep. Yep. So this one needs to be changed to strf underscore size. Why? Because Y is not a pointer to a structure. X is not a pointer to a structure. X is a structure. So the local variable X takes up the same number of bytes that the entire structure strf will require. So that's why we need to make that adjustment so that there are enough bytes between X and Y in this case. All right, and then LBS is done correctly because Y is only an 8-bit thing. So it is just 1 byte. Okay, we're all good. We do the allocation on line 250 and 251. And then I automatically check for the end first. So we do the deallocation, and this is the code to return to the caller. Okay, that looks all good, which means now we can go into the main subroutine, starting with starting on line 255, which is supposed to implement line 79 of the C code. All right, so this time I start with the left-hand side. So that's why I said earlier, there's no set pattern. Am I going to deal with the left-hand side first or the right-hand side first? It kind of depends. So we have the offset, we have the address, and then we have the right-hand side. So the right-hand side is Oh, right, so this is the offset of the member N, and then we added to B. B is the address of local variable X, which is a structure. So register B is now the address of member N of the local variable X of main. So that would be the explanation. So register B is the address of X dot N in this case. Now, if somebody, somehow relate X and N, but put a pointer here, that would be a partially correct answer. Because X is a structure, X is not a pointer to a structure, so the use of a pointer would not be correct. It has to be a dot in this case. Yes.
Wait, why at that point is it the value N of X? Wouldn't it be after add BC?
Oh, right, yes.
Okay, thank you.
You are correct. Okay. Thank you. So this would just be the address of X, and then by this time, it would be the address of member N of X. You're correct. I put the comment into the wrong place. Yes. Thank you. All right, so are we good so far? Okay. And then line 261 is just dealing with the right-hand side. We have a very simple concept of great. Yes.
So on lines 255, 256, and 259, where the question marks are, on the exam, you would want us to replace the question marks with what the contents would be on for every single one of those,
Right.
not just one statement.
That is
afterwards.
Yep. But you can do it in many ways. You can just kind of write it in empty space and then just use an arrow to point to the question mark. Yeah, so that way you have a lot of freedom in terms of where you want to put the answer. As long as you can relate your answer to where it's asking, it'll be fine. Yep.
Like the structure of the test, is it gonna be on one page next to each other like that, or are they gonna have separate cadence?
It's asked a little bit earlier. I think this time, because it's a one paper test instead of a online test. I will give you the C code separately on the page. So this way you can tear out the C code page and then makes it a little bit easier to relate to the assembly code. Flipping. I mean, yeah, a little bit. All right. And then we store the right-hand side to the left-hand side on line 262. We good? So now we move on to the next one, which has a very similar structure, but the way it's done is different. Okay. So now we do something with register C. Okay, we are adding something to register B, which is the content of register C. And then the question is that right? So the question is, what was the value of register B the last time we changed it? What was the last time that we changed it? What is the line number that we changed register B the last time? 259. And according to the answer to that question explained in C concept, what is in register B at that point? The address of member N of X. Okay. So we are now doing kind of the same trick here. We are basically looking at the number of bytes between member K and member N. Okay, and we're adding that offset to register B. Register B is already the address of N. So that means after the addition, B will become the address of K or member K of the same structure. So the way I answer this would be B is now the address of X dot K in this case. Okay. All right, that seems to be what the left-hand side on line 80 of the C code is referring to. So we're good there. LDIA with 2, that seems good. And then we store A to B, which is the assignment. I think we're good here. All right, so now we just have to call F with X. So let's see if this code is doing what it is supposed to do. So we'll go ahead and scroll up a little bit like that. All right. Line 272 is loading the offset into A. We are now line 273 is computing the address of X. we decrement D, we push A on the stack. Is that pushing the address of X on the stack? It is.
Oh, yeah.
It is pushing the address of X on the stack, offset address of push. So we are indeed pushing the address of X on the stack. And then we try to push the return address on the stack. And this time, it should be a .6 plus. So we change this to a .6 plus, 5, change to 6, there we go. But I still have to double check everything, make sure it is the right register that got pushed. Decrement D and the store register A to where D is pointing to, so that is pushing the return address on the stack. Continue execution at function F. When it returns, we just kind of go to the exit code right away. Or we store the value into Y. Aren't we forgetting something? What are we forgetting? Increment D. Why are we supposed to increment D?
Yeah, okay.
Yep, because we have an argument on the stack. So does that mean that we need an increment D always after a function call? Nope, because it depends on whether we have arguments or not. Okay, so that's important. All right. All right, so that computes the right-hand side of line 81. And then we have to deal with the left-hand side. We have the offset address of, and then we do the assignment. Looks good to me. And then we have the return value of main itself, the allocate the local variables, and then returning to the caller of main, which is all the way from the beginning. So this seems to be it. And we have 3-4 minutes left in this class, which means in the final exam, I would have what? It's a 2-hour exam. I cannot do arithmetic. 20 plus 3, 23 minutes. Okay, but are we really sure this code is doing what it is supposed to be doing? Now, since you cannot have access to a C compiler, GDB, or login, I do not expect you guys to be able to run this code. You cannot run this code, okay? You can run it in your head. The C code you can kind of run in your head, but even so, that may be a little bit too much. But we are running a little bit out of time. I can run this in River Spider right away and actually see the result. Yep.
I think you did the arithmetic wrong. I think it would actually be 43 minutes because the class is only 80 minutes long.
Right.
So you spent 77 minutes.
Yep, because in my head, 120 minus 80 is 20. You go like, what base are you using to get that kind of result? What base indeed will give you that answer? 120 minus 80 is what we know as 20. Okay, so I'm gonna leave you guys to kind of think about this. I think it's a base 5. No, it's not base 5. I don't even know whether there's a base that can do it. Anyway, all right, but regarding the final exam, do we have any questions about the, yes?
So the final exam is it this and other concepts, or is it mostly that?
It would be all the concepts that we have talked about in class. Mostly it is revolving around a few things, okay? The agreement between the caller and the callee is probably the most important part, okay? And how the stack is utilized and the instructions that you use to access various things, okay? In other words, we look at the C code, we go like, okay, how do we do this, right? That is, understanding the C code is the first thing, but that's why CISP310 is the prerequisite of this class, okay? And the other thing is to go back to the assembly language code and be able to understand what this means. What does it mean? What does this mean? What is the difference between a CPR and an LD? Okay, because they look always the same, okay, because of our 2 registers, and it seems like we're copying something from a register to another register and sending it to ST. how are those instructions different? And I certainly hope you guys get all that down by now, because otherwise we're in kind of big trouble. So what, after that is done, then we look at sequences of instructions and say, if I look at these two instructions, what do they do? Okay, between line 282 and line 283, we got the offset and we got the address of y, which is local variable of main, and it is supposed to be sitting on the stack. Okay, so it is basically a accumulation of all of these things that we have talked about since the end of exam 2. So does that answer your question?
So this entire thing about finding all the bugs and then replacing them with what's exactly what the, that will take up the majority of the test.
This is the entire test. This is the entire test. I will still allocate a little bit of time to read the instructions carefully, but I don't plan to change the whole thing. But it would still be helpful to read the instructions. Yep.
You compose the code.
Absolutely, and one more thing, the diff, okay, I forgot about the diff. Okay, so let me do this, okay, I know we are using some extra time, but since we don't really have a structured lab activity today, I think we can just spend a little bit more time here. All right, so let me get back to this code here, and then re-download this as a different file this time. So I'm gonna download this as fx1.btp ASM. There we go. All right, so if you're using Linux, you've got a few tools. Even if you're not using Linux, there are tools that are on the web that can do the same thing. So yeah, Vim turns out to be able to do something like this. So you can do it like this, fx1 on one side, fx on the other side. And it'll give you, okay, the color scheme doesn't work well in this case, but it'll give you a comparison, where you inserted extra lines and stuff like that. There's also just simple diff. And that will tell you whether we have inserted something, whether we have deleted something or not. Now, for those of you who do not want to install anything or switch to use Linux just for this class, I can understand that. You can say, you can just search for visual div web interface, okay? And then we have web checker, compare text online to find the difference. All right. Well, as long as you're not sending over your business plan for something, I think this is going to be okay. So we'll say cat, this is xclip-south. We'll use the original one on the left-hand side. So that's fx1.
I've actually used this before. You can drag and drop files.
Sorry?
You can drag and drop files.
Oh, you can just upload the original text. Okay, since I'm here already. All right, so this one I'm going to upload just to see whether that works or not. There we go. All right. And then it says find difference. And there we go. It's color-coded here. And it's even, this is basically an overall map. So you can move the window into that region, and it will tell you that green is inserted. We got a bunch of insertion here, and then we have a change over here, and so on. So once I upload the finished program, then you can use the same tool to do a visual compare. And I think this is a pretty good, useful tool. And then for every difference, you probably want to kind of make sure that you understand what the difference is, what bug is it fixing, and so on. Yep.
So can you post the C++ code as well?
That is in the attachment already from. That is in the announcement that is titled final exam. So it's in the C code is embedded into the assembly code. I can clean it up and separate it if you need to, but it's there already. Yep.
You're sending over like the before code or the after code?
I am sending the after code now. The before code is right here. This is the before code. All right. So let me finish this last part. So we do not have a structured lab activity today. Neither do we have any on Thursday. But I will be at the lab today in case you want to work on your program or you have been working on your program and you get to the point where I have no idea what is going on. The program is not doing anything that I expect it to do. Then I can come take a look and see if I can help. Yes.
Thursday, we're just gonna talk about the solution of the assignment.
On Thursday.
Yeah, is that all we're gonna just talk about today?
Yes, but that I have a feeling that it might take up the entire class, depending on what kind of question I get on that day. Because the point value, as you might have noticed, is really low compared to something of that complexity. That was intentional because I don't want to make this like a 20-point homework assignment. And then people cannot get it working and they start to worry and they start to go like, like that. I really want you guys to really just give it your best try, okay? And in the process, if your program doesn't work, that is actually teaching you more than getting everything done, working the first time. Because when your program is not working, you have to debug it. So unless you're using a randomized change to your debugging technique, which I have observed even at UC Davis, if you're using a logical, rational way to debug the program, the process of debugging is actually in this class the best way to study the material. You say, okay, my program is not working. I know what it's supposed to do in C and also in assembly, but it's not doing it. What am I missing? That is actually one of the best ways to study the material in this class. So that's why it's a low point value homework assignment. It does not mean it is not important because the final exam is 40%. That's a good chunk. So that means the attempt to do the homework is my way of encouraging you guys to study and understand the material. So I'll let you guys go first, to the lab, and I'll be there as soon as I clean up over here and post the solution on Canvas. Yep. Hold on. Let me turn off the recorder. Unless you wanted to be recorded.